So, we will continue what we have left in the last lecture. So far, we have covered engine operation, transmission types, ray diagram, kinematic diagram, number of teeth in each gear, gear failures, gear material selection, and we have been doing model calculation, and we will continue the model calculation for today's lectures as well. And if you look at, this is the problem we given, and it's a constant mesh, okay, and these are the gear drives, the things. More importantly, we should know this is your power, and the 1 Newton meter is the torque, okay, 1 Newton meter is the torque, yeah, at 2000 rpm, okay. And what we did, we have completed all the things. We need to select the materials now. We have to select the materials and do the module calculation. I am sure this is the equation I have shown in the last lecture. This is the fundamental equation. Lot of correction factors for bending aspect, and from here we move on to the pitting stress AGMA standard. Again, these are the various correction factors aspects is given, okay. Finally, what we have done, and this is about the based on the strength equation for the material aspect, and again we discussed for the what is the yn, y theta, y z, sf is the factor of safety for bending aspect, and similarly for pitting we have done this also. You can say zn, zw, y theta, y z, and sh would be the factor of safety for pitting stress. Then based on this, what we have done, we made a lot of these k values as a k total for simplifying, and finally we got a model equation 2t k total sf, within the bracket this is design value bending, psi is the structural support or frame factor, right, y is z is the number of teeth, I am sure you would know, and the corresponding the material strength equation, and this is the equation we got, and corresponding this is for the pitting aspect, this is for this equation for the pitting strength, pitting, wear resistance, what else we can say, wear failure, what else, any other thing, contact, you can do the contact also, right, contact aspect also, yeah, that is correct, okay. Now, so now we will go for the each and every aspect. Maybe if I look at the previous slides, we have to find out, we should know what is the torque value, k total, the factor of safety, z square, sigma c whole square, psi values, your number of teeth, and another geometry factor. Similarly, we should know about what is that SC corresponding Zn, Zw, y theta, y z. These factors we should know. This is applicable both bending as well as pitting, okay. Yeah, but I will give a general information, then later we will choose pitting alone. I will give the reason also why would we choose for pitting aspect, right. So, as a design engineer, you have to choose the material, okay. So, this is material based on the bending strength. So, you have to look at the hardness aspects, what of a surface treatment are you going to choose, the grade, there are two different grades, one is precision of the grade, the other one is quality of the grade, both aspects you need to understand. How to find, you can use various charts, tables and equations, and this is from I have taken from Shigley book. You can see that sometime they will give this is the hardness I need, right, this is the treatment. So, when you have a through hardened steel some 300 BHN and grade is given, you should find out what would be the your bending strength. Suppose someone gives you saying that 300 BHN, right. So, 300 BHN correspond grade 1 material, you can choose from here either way, otherwise use this equation. This is for grade 1 and the corresponding you can use the grade 2. This is in a PSI, are given in a SI units. So you substitute 0.703 into 300 plus 113 will give you strength of the material. This is one way to for the through hardened steels. Similarly, you can find out for the ASI 4140 and 4340, which is nitride through hardened steels. Same, depends on the what is it hardness, that also you can do. So please understand from the previous slides what we did. So this is given as Brenell hardness. This is given a Brenell hardness. When it's given Brenell hardness, it's about the covering things. And if you look at here, this is given the core hardness. So when you give the heat treated entire sample, the entire sample should be heat treated. That's why it's called core hardness. Sometime if you do the selective induction hardening, right, or flame hardening, that will strengthen the only the profile aspect, not the inside. So you should understand what does it mean, the core or through. Okay, that's the difference. You would are able to see that now. Okay, and this again for nitride steels also. We are again various grades, grade 1, grade 2, different increasing chromium component level. Then usually you have to choose for meeting at least 10 million cycles, 10 power 7 with the reliability 0.99%. This is another table, you can choose it. This is for iron and bronze gears. Again, always choose for minimum of 10 million cycle, that is the life cycle, fatigue life cycle for the gear. With the reliability rate, reliability it may means if you have 100 gears, so 19 gears should be able to meet 10 million cycles. One gear can fail, so that's called reliability. Yeah, like Elton life in bearings. Right. Now we'll go for the temperature factor. Okay, temperature is very crucial. Y theta for oil or gear blank temperature up to 120 degree, you can choose Y theta here. So look at the equation. Our equation we had, so here we can choose Y theta value as a 1. Please note it down. Okay. Now for higher temperature you can have the more value. These are the correction factors. Right. Now we talk about reliability factor as I discussed earlier. Accounts for statistical distribution of material fatigue failure aspect. This is standard equation and is available. If you have a higher reliability, your factor Y is it which is SI is in SI units within the bracket. So you could see that higher the reliability, your correction factor also will increase obviously. So reliability higher for watches because you need to have a very high precision, that is also there. Depends on the application, how do you want to. Usually we go for automobile application, your Y is equal to 99%. If it is sufficient, that would be alright. So Y is set we can choose as a 1. Okay, it's unless specifically is given. Then of course these are the bending. I will do it same for the pitting also. Yes, look at this. This is nothing but your SN curve, right? Number of cycles on the x-axis and stress tensile factor on the y-axis. So I always said whenever you go for gears, you should go for the minimum of 10 million cycles. So if you look at, if this is the life you want to have it, right? So you should use what is the yn value. Of course, and if we move this one, better to choose the upper curve. Better to use the upper curve because that's give you more safety. Again, this depends upon the pitch and velocity, gear material cleanliness, residual stress and material ductility and factor toughness aspect. So anything beyond that, right? So what happened? Your stress strain will be reduced, right? So in fact, this is anything. This is a low cycles up to 10 power 3, and anything beyond 10 power 3 will be higher cycles, fatigue cycles. Okay, standard. So here this is the standard one. Yeah, this is for the yn. So we can choose straight away as a yn for bending. Yn we can choose as a n equal to 1. This is for bending aspect. Now we talk about pitting strength. Pitting strength similarly. Okay, look at this. Yeah, earlier you have seen the hardness is a smaller value, but here is the hardness for either for a grade 1, grade 2 will be higher, they are less than 1, 0.7, right. Look at this part, this is 2.2 for grade 1, and higher the grade better material 2.41. This is again through hardened steel, and this is for the steel gear with the other aspects. We are talking about contact field strength for 10 power cycles with the reliability of 0.99, right. If various hardened, you can through hardened, flame induction, carburized, nitride again, so many aspects. Okay. Now stress cycle factor, as we did discuss for bending, this is for your Zn for the pitting aspect. Similarly, you can see that the x axis for the number of cycles, y axis for the correction factors. So as usual, we want to choose for the 10 power 7 with the reliability of 0.99. So in this case, your Yn would Zn here, the Zn I would assume take it as a n1. Okay. Look, so when you have bending, only the 4 parameters are involved. Now for pitting, you need to know what is the lubrication regime. We will discuss when you go for a lubrication aspect, the failure criteria, it depends on okay, smoothness of operation, pitch and velocity, gear material cleanliness, material ductility and resources. These are already there for bending. Additionally, you have to look at, because this is nothing but the wear failure also, right, wear failure or else contact failure or else what else, pitting failure, are related to lubrication. The bending nothing to do with the lubrication, this is above the stress for the, right. So the tooth breakage on this aspect. So that is why the top 3 are very critical for pitting, right. Hardness factor, so this is generally applicable for the gear. I will tell you why is the reason. You have a gear, you have a pinion, right. One rotation of gear, how many rotation you would expect a pinion? At least 1 or greater than 1. So that means the pinion will go take more turns compared to your gear. So what happens when the pinion undergoes more turns? It will go to strain hardening. The moment it goes to strain hardening, what happened to the hardness? Hardness will increase. Okay. In general, as a tribologist, we always say that we don't have a 2 equal hardness material. If you have 2 equal hardness material, both component will damage. Okay. How will you cut diamond? Why can't be less than a diamond? You said diamond has to be cut by diamond. Why can't use some other material? What happens if you use some other material? That material will break, right? It will give the damage. Okay. So we have to have as close as possible, but there should be a little away. We can't have a 2 equal hardness. That is a basic thumb rule for a hardness aspect. Okay. So that is why. So the pinion is generally subject to more cycle than the gear, since it is a fewer teeth, and both are hardened by the same process. The one can actually harden the pinion alone little more, so that the work hard will make. So higher the harder, what happen? It will affect the softer material. You don't want to happen. You have to be careful to choose certain ratio, such way that you can maintain one gear safer, one component will be safer, other component will be failure. Okay. Let me ask question. So when I say gear aspect, I will put it more of which will create a bigger, which will have a component bigger size, more expensive, that component should be protective than the another component. Either it could be cost aspect, it could be size aspect, right. So based on that you can select the materials. Yeah, particularly I am talking about the hardness aspect. Okay. ZW is applicable. So we will choose as a ZW equal to 1, and this is the equation we are, because we are concentrating the gears from the lathe shaft transmit the power to the output shaft. So it is a lathe shaft, gears are pinion gears. So this is applicable for only the gear. Yeah. Okay, this is another important parameter for the elastic coefficient. It's called, another term is complex coefficient. This is again due to contact mechanism, due to the contact mechanics or contact between the two gears, the surface contact. So, which again it depends upon the your Young's modulus as well as your Young's modulus of the pinion and gear and Poisson ratio. Okay, Poisson ratio. These two parameters are very critical for this. So, where you can see that the Poisson ratio of pinion and gear. Similarly, EP and EG are the Young's modulus of the pinion and the gear respectively. And you know, to use the equation, already we have a chart here. This is taken from Shigley. So, look at this value. So, anything within the bracket is SI unit, outside the bracket is a MKS unit. Assuming you have taken the steel pinion, okay, which is 2 into 10 power 5 MPa, then you have taken the steel gear, which is 2 power 10 power 5, always the Poisson ratio 0.3. So, if you substitute, you would expect this is the equation, this is the value. So, ZD equal to 191 square root of 10 power 6. Look at this, this is star is given. Look at this. The supposed to be the new if you substitute within the equation, this is what you will get it. So, 191, if you do the 10 power 6 square root, that is a value you would expect ZE as ZE value. Okay. For us, in the equation, pitting equation, that will come as a Z square E. When you have Z square E, it should be 191 whole square into 10 power 6. This is the value, 191 into 10 power 6, 191 square into 10 power 6. This is the value we should substitute. Now, surface condition factor again depends on the smoothness, because these gears are lubricated. Okay, these gears are lubricated, smoother surface is better. So, you can see that cutting, shaving, lapping, grinding, no, it should be honing, this should be honing, there is a typo error, should be honing, this is very precise things. So, this is there is no established, you can always choose ZR equal to 1, we make it as a simplified ZR equal to 1 in our calculation. Right. Now, I will show the actual materials. So, either the hardness given, the grade is given, you have to choose the material, that is one other way. Otherwise, you can choose from in this table and move on. Okay. I think I have already explained this table aspect. This is your not sigma H, I would say SC, and this is sigma nothing but ST. Okay. Yeah. So, always ST is 3 times lesser than the ST, 3 times lesser than the ST. In that case, can we look after for the bending aspect or pitting aspect? I am talking about model calculation. Can we do based on the bending stress aspect or contact stress aspect? Contact, obviously, because of your bending stress 3 times lesser. So, even if you take care of contact, that is taken care of bending as well. So, better go for the model calculation based on the pitting stress aspect. So, here there is no specification given for material selection. Since automobile application, I will go for the 42 chromium moly. Okay. Chromium will give you wear resistance and corrosion aspect also, right. And moly it's a give you nice lubrication. Molybdenum is another good material for lubrication aspect. Again, this is the steels only, the steels. So, I have choose this is the material. So, in that case, my SC would be 760 into 10 power 6 Newton per meter square. SC would be okay. And similarly, ST would be 220 ST equal to 220 10 power 6 Newton per meter square. These are two values. Yeah. Now, So you know the equation, right? You know the equation. Your sigma c within the bracket. Can you have the equation, please? Sigma c equal to st yn, okay, and y theta yz. St value we know 760 10 power 6. Other value we chosen as 1, so there is no problem. Your sigma c will be equivalent to st, which is nothing but 760 10 power 6 Newton per meter square. That's the value is given. Yeah, that's fine. Now we'll move on to the next one. Yes, this is a very important. Frame factor or structural stability, right? Frame factor or structural stability, which is taken from Damir Jalska. You can see this is the reference I have taken, which is critical. The gearbox purpose is not only transmit the power and also should give you support, right? How does it give support? We can see this is the, if you have only the teeth alone, casting teeth without any other support, a frame support or bearings, then the psi value you take it 7 to 10. If you have cut and ground teeth with the frame support 10 to 15, cut or ground teeth with the both sides you have a support with the gears, right, then 15 to 25. Ground or shaved teeth both sides support gear shaft in gearbox, properly lubricated, and if the prime mover operate less than 3000 rpm, you can choose 20 to 45. Okay, same thing, but if choose if it's operate more than 3000 rpm, then you can go for the psi value 30 to 100. Okay, so what is our case? We want our smooth transmission, right? We want our smooth transmission. So obviously gear should be either ground or shaved teeth, and also we will have support with the bearings, right, through shaft, properly lubricated. What is speed operation? 2000 rpm to 4000 rpm, right? 2000 rpm to 4000 rpm. So in that case we should choose this one. Okay, so maybe I will choose at the lowest value psi equal to 30. I am choosing the psi equal to 30. That is the value I am choosing. Yeah, taken. Then another way also you can do based on the your B by D ratio. Okay, so psi b is given. So it depends on the how you wanted to. This is, you can look at this based on the what is the material and corresponding treatment. The B by D ratio also given, right. Then very important, right. Are we use the phase width constant or variable? We know psi equal to B by m, right. Psi equal to B by m we have chosen, right. This is what the equation. Would you expect the phase width would be same for all the gears or variable? Remember, in automobile application we want to reduce the weight as much possible. Okay, if you keep the phase width same for all the gears, right, it will be heavy, which we then fuel consumption will be more. We don't want to, right. Look at the first gear will have a high torque because your speed is low, right. Then as you move on to the higher speed, your torque will be reduced. So another thing is in that case, so wherever the torque is more, the stress is more, there you can have a bigger phase width, as reducing the torque and stress you can have a smaller phase width, right. Interestingly, you can look at this is the ratio B by D ratio. You can see that D is the pitch diameter, okay, and is given between 0.6 to 0.8, and if you choose for second it is even lesser, 0.4, and 0.3 for the third, then you can again same range, 0.3, and this is I have taken the automotive transmission system, and you can see there is in the range, you can see that these are in the range. Okay, so that's a one way, a good thing is in our problem we are going to change the phase width for each aspect, right. That is how we are going to do the problem. Yeah. Then another thing is a gear phase speed in terms of module and center distance, right. This again another equation, this B by D raised aspect for various accuracy and mounting support. I will skip that. Now we will go for the equation, right. Yeah. So will equation m cube equal to 2t k total of C, right. ZR divided by sigma C square whole square J square psi then ZI. ZI is missing. Okay. So question is, we need to find out what is the torque here. T max is given what, 190 Newton meter, right. T max given 190 Newton meter at 2000 rpm. Yeah. So what happened torque here? Are we going to use 180 Newton meter or some other value? Remember, this is coming from the engine. This is coming from the engine. The moment is coming from the engine from clutch input shaft, then you have reduction of by 2, right. The speed is reduced half of that to the lathe shaft. Then what what is the torque value at the lathe shaft? Will be 2 times 180. Okay, so the T would be 2 times 180 Newton. Okay, that should be 380, right. Yeah, 380 Newton meter. Okay, that's the one thing is there. Is it clear, right? Yeah. So we assume this K total as a we'll simplify that, otherwise it will take more time. That's the one. Okay. Then what happened? Sigma C square already we know. Sigma C value equal to what is that value? 760 into 10 power 6 Newton a meter square. That we already know that. Then right, jets E square. What is the jet ski square? 191 whole square into 10 power 6. That's we got it. ZR we have taken as a equal to 1. Okay, equal to 1. Then psi value we is to choose as a 30. Psi value we choose as 30. Then two things are remaining, Z square and ZI. Okay, Z square and ZI. Okay, what is Z? What does mean Z? It's a number of teeth. It's a number of teeth, right? So we always talk about drive by driven, right? So what is the lowest gear will have a more stress? Lowest or smallest gear? Gear 12. Gear 12 on the first gear. Look at your kinematic diagram. Can you check your kinematic diagram? It's a gear 12, right? That has a minimum number of teeth. Okay. And one more thing is, I also mentioned that, so since some of the gears coming 14 and 16, we should double it. We should double it. So what happened then Z value now? Z is nothing but, let me write, Z is nothing but your gear 12, right, which has a 18 into 2, 36 teeth, 36 teeth, right. So Z square should be now, what is the Z square value now? 36, okay, that's the 6, yeah. Then we have to find out, this is the surface indicator. I will write down the equation, right. Zi equal to cos into sin phi by 2 into Ig by Ig plus or minus 1. This is the equation. This is the equation. This is again for the gear type is external arrangement, right? The gear type is external arrangement. For external gear, you should use plus. fractional gears use plus, for internal gears use minus. Okay. So, question is what is IG value? Which IG value you have taken? There are so many IG values are given 1, 2, 3, 4, 5. Which we should use it? We should use it for gear 1 because we are doing calculation based on the minimum number of things. So, 3.545. Okay. So, what is the pressure angle we have assumed at the beginning? 20 degree, right? Pressure angle 20 degree we have assumed it. Okay. So, can you substitute and tell me what is the value you are getting? ZA equal to, remember this equation applicable only for spur gears. If you have helical gears, then you use different equation. Okay. So, this is applicable only spur gears. Can I have the ZA value? What is that value you are getting? I think something 0.125. You should expect 0.125. Okay. We substitute cos 20 into sin 20 by 2. This is 3 into again into 3.545 by Ig plus 1 4.545. So, I think it should come 0.125. This is the value you should expect. Is it coming? Right? Yes, coming 0.125. Well done. Now, so now we have all the values, right? We got all the values. Okay. We have all the values. So, can you substitute and tell me what is that you are getting the model equation? So, what is the model value you are getting now? You have to tell me, please. Yeah. So, you have to substitute everything in cubic equations. Okay. Substitute in cubic equation all the values. The model will be in meter, and you have to tell me in millimeter. Do you want to know the equation? Values, yeah. T equal to 360, right? Yeah? 380, 3 equal to 380. One more thing is, we missed one thing. We have not, what is the factor of safety we are going to use it? The factor of safety. We have to take this S square H, use S square H factor of safety as a 1.5. I am taking as a whole, as in terms of square time. Okay. So, for factor of safety 1.5, what would be the corresponding module value? So, this is a factor of safety. This is a factor of safety for pitting. Okay. So, by substitute you would expect the model value something, sorry 2.412. Okay, thank you. 2.412 is the your model in millimeter, 2.412. Okay, 2.412 is the module. Right. Can you choose straight away that model value just like that? No, you can't use it. So, what you need to do? You have to go for the standard model value. Look at this. Look at this. Okay, you have a preferred. This is the first preferred series. You should always prefer this one. If you don't have any other choice, then you go for second choice. So, 1.25, 2, 2.5, 3, those things given. But we got value was 2.142, right? 2.412. So, in that case, can you choose module as a 2.5, right? Mm, yeah. So, from table we approximately we choose as m for the standard aspect 2.5 mm. So, this is the model calculation we have done that. Okay. So, let me ask one question. So, this model should be same for the meshing gear also, right, for the first gear. How about gear 2, 3, 4, 5? Can we use the same model or different model? Same. Okay, but they are independent, right? They are independent. Yeah, you can choose the same, because so then it's easy to pick up. Otherwise, it will be laborious to again calculate a model for the individual gear mesh aspect. Okay, and this is the one. So here you have freedom. There is no restriction is given. There is no restriction given. When I say there is no restriction, if they give the center distance, how will you do that? That's a question, right? The center distance given. This is center distance equation. Again, sometime in the problem you may given the center distance, then based on the center distance you have to find out the model. Okay, so that will be the constraint, right? Here, as a first problem, I did without any constraint, whereas in the assignment I will ask you to do based on the center distance method. So you should derive the equation. What is the center distance equation? Smaller equation. If you know that and corresponding to full replace with the module, you will get the complete whole equation with the gear ratio aspect. Then try to solve the problem. Okay. So I hope now it's a major chunk of the gearbox aspect finish. Now we'll go for the face width. Then the other things are very common. When you say other things are, you know the have to calculate shaft diameter, right? Calculate shaft diameter, bearing selection. Those things I will touch very quickly, then we will move on to the brakes aspect later stage. And yeah, thank you. We will continue next class.